worksheet 10, chapter 14, heat. So hopefully you can see this. I suggest that you have the solutions beside you and follow along if it's not very clear. Okay, first question is convert 385 joules per kilogram Kelvin into units of calorie, gram, degree centigrade. It's a simple unit conversion question. I guess the important part in this is that we have per Kelvin and I want it into per degree centigrade. But per Kelvin, it's a change in temperature. And whereas the Kelvin and centigrade scales have different 0 points, the actual size of the degree is the same. In other words, a change in temperature in Kelvin is equal to the same change in temperature in degree centigrade. This isn't true in Fahrenheit. The freezing point of water is 32 Fahrenheit, the boiling point is 212 Fahrenheit, so there's 180 divisions on the Fahrenheit scale between freezing and boiling, whereas there's 100. So you can see that the Fahrenheit, it's a finer division than the Kelvin or the centigrade, but the Kelvin and centigrade are related to each other. The relationship is that the division size is the same. And as this is a change, for the Kelvin, I can just write degree centigrade, it's the same. The question then becomes somewhat simple. I have joules, I want to convert them into calories. We went through we've discussed this. This is called the mechanical equivalent of heat. And then I convert kilograms into grams per gram here, and out pops the answer. Okay, easy enough. Question 2, when a diver jumps into the ocean, water leaks into the gap between the diver's skin and her wetsuit, forming a water layer about 0.5 millimeter thick. Assuming the total surface area of the wetsuit covering the diver is about 1 meter squared, and that the ocean water enters the suit at 10 degrees centigrade, and it's warmed by the diver to skin temperature of 35 degrees centigrade. Estimate how much energy in units of candy bars is required by this heating process. Well, first of all, we can get the volume of the water. The volume is the area times the thickness. The area is a meter squared. There's 0.5 millimeter. So that's the volume of water to be heated. The mass of that water, well, density is mass over volume. Mass equals density times volume. There's the density of water. There's the volume of water, 0.5 kilogram. So about 0.5 kilogram of water enters into the wetsuit. How much energy does it take to heat this up? Well, here's our specific heat capacity equation. Q equals mc Tf minus Ti. The final temperature is 35, the initial is 10. We've got the mass, we know the specific heat capacity of water. There's how much energy we need. All we have to do then is convert this energy joules into calories, and then we convert it into candy bar. One candy bar is 300 kilocalories, which is the big calories, and that gives me about a 20th, isn't it? That's about a 20th of a candy bar to heat the water up, right? So if you eat a candy bar, you're not going to lose the weight by sitting in a cold bath that quickly. Okay, question 3. Let me just scroll this up here. Remember, again, I've got this note up here. We have the food calorie, which is a big C, and the physics calorie, which is a little c. So it is a little bit confusing. Okay, an average active person consumes 2,500 food calories a day. Okay, you probably know that. What is this in joules? Okay, so 4186 joules is one big calorie. That's about 10 to the 7 joules. B, what is this in kilowatt hours? Well, we know kilowatt hours 3.6 megajoules, so that turns out to be about 2.8 kilowatt hours. Part C, if your power company charges about 10 cents per kilowatt hour, how much would it cost if you could just plug yourself in? Well, okay, 2.8 kilowatt hours at 10 cents per kilowatt hour, about 28 cents. And then could you feed yourself on this much money per day? Yeah, well, maybe if you ate only rice and beans, you'd be struggling though, even eating only rice and beans, so probably not. Okay, question 4. A small immersion water heater is rated at 375 watts. Estimate how long it would take to heat a cup of soup. Assume this is 250 milliliters of water from 15 to 75 degrees centigrade. Okay, so I think what we need to do here, power is energy over time. Time equals energy over power. We need to work out how much energy it takes to heat it up, divide it by the power, and that will be our answer. Okay, so starting off, how much energy does it take to heat up the soup? We're going to assume no heat is lost during the heating process, so this will be a lower sort of estimate. Q equals MC TF minus TI, 250 milliliters. Well, we know that the density of water is 1 gram per milliliter. That's 200.250 kilograms. Specific heat capacity, final temperature, initial temperature, 62.8 kilojoules. Power is energy over time. Time is energy over power. We throw the numbers in, about 167 seconds, which is what, about 3 minutes to heat up the soup. Okay. Question 5. What is the specific heat capacity of a metal substance if 135 kilojoules of heat is needed to raise 4.1 kilograms of the metal from that temperature to that temperature? Okay. Well, we have Q, we have M, we have TF, TI, we want C. Here's our equation that relates those quantities. C, that's what we want. We solve it algebraically, and then it's just a case of putting the numbers in to get the specific heat capacity of the mystery metal. And we could figure out which metal it was based upon this experiment. Question 6. What will be the equilibrium temperature when a 265 gram block of copper at 245 degrees centigrade is placed in a 145 gram aluminum calorimeter cup containing 825 grams of water at 12 degrees centigrade? And I've given you the two specific heats. Okay, so we have to consider what happens here. Let me just see if I can move that along a bit. There we go. Okay, so here's my chunk of copper being put in some water in this cup here. This is hot. This loses heat. The water gains heat. The container contains heat. But because this is an isolated system, overall, all of these heat exchanges add up to 0. Okay, so I can say that the sum of the heat exchanges is equal to 0, and then we start writing them down. Mass of the copper, specific heat of the copper, final temperature minus the initial temperature of the copper. Right, now if you think about it, the final temperature of the copper, it's going to cool down. This term is negative, isn't it? Because TF is smaller than TI. So the negative indicates that heat comes out of the copper. And then we've got the water, final temperature minus the initial temperature. Well, for the water gets warmer, so that term is positive. So that term is the heat flowing into the water. And similarly, this is the heat flowing into the calorimeter cup, the cup in which the water is contained. All of those heat flows have to add up to give me 0. So what I have to do is to solve this for TF. It's not that hard. You expand out the terms, all of the terms without TF, shove them on the right, and then take TF out as a factor and divide it by the stuff that was being multiplied by TF, right? Then what you have to do is put in all of the values, and this is where it gets messy. I've always said try and do calculations in one fell swoop on a calculator. In this case, you honestly might be better off just somehow making a table and doing these terms individually, breaking them down. These questions aren't difficult, but there's always a lot of numbers flying around the place, and it gets a bit messy at times with all of the values. Okay, I evaluated the top, I evaluated the bottom, and got 18.5 degrees centigrade. Okay, so it's conceptually it's an easy enough question, but practically you want to be very careful with the calculation. Question 7. The 1.20 kilogram head of a hammer has a speed of 7.5 meters per second, bang, just before it strikes a nail and is brought to rest. Estimate the temperature rise of a 14-gram iron nail generated by 8 such hammer blows done in quick succession. Assume the nail absorbs all the energy. Okay, and I've given you the specific heat capacity of I in there. Okay. Well, the energy Q absorbed by the nail will be 8 blows times the kinetic energy of the hammer, which is 1/2 m mass of the hammer and the speed squared of the hammer. So the nail absorbs 270 joules of energy. Q equals mc delta t, and in that case we have delta t, which is what I want, is Q over mc. I've got all of the numbers, I put them in. The nail will become about 43.5 degrees hotter, right? If you ever pulled a nail out of something, you'll notice it does become appreciably hot. Okay, question 8. How much heat is needed to melt 23.5 grams of silver that is initially at 25 degrees centigrade? Okay, well, this question is a little bit trickier because now not only do we have heating, we have a phase change. So there's two things involved here. First, we have to put energy in to heat the silver up to its melting point, and after that we have to put the energy in to get the silver to change its phase, to change phase. So the heat needed to get it up to its melting point is MSCS TF minus TI. That's my initial temperature, there's the melting point. So it takes 5.28 megajoules to get it up to its melting point. And then the heat to melt is the mass of the silver times the latent heat to fusion, and that's 2.61 megajoules to melt it. So the total energy needed is just the sum of these two, which would be 7.89 megajoules. Yeah, okay, so easy enough. Okay, question 9. What mass of steam at 100 degrees centigrade must be added to a kilogram of ice at 0 degrees centigrade to yield water at 30 degrees centigrade? Yeah. So basically I'm getting steam, I'm adding it to ice, and I want to generate water at 30 degrees centigrade. Okay? Well, when the steam condenses, it releases a certain amount of heat, and that's given by MSLV. Now, I had to add the minus sign myself. So when you're doing the latent heat of vaporization of fusion, you have to think about what's happening and add the sign. The sign doesn't automatically become right. With the normal specific heat equations, yeah, the sign works out correctly. Here, I had to put that minus sign in because as the steam condenses, minus heat comes out of it, right? Once the steam condenses, it becomes water at 100 degrees centigrade, and that is going to release heat as it cools down to the final equilibrium temperature. So that will be MSCWTF minus 100. Now, again, look here, I haven't put a minus sign here, but the final temperature will be 30. 30 minus 100 is negative. So again, this term here is negative, indicating that heat is released by the water at 100 degrees centigrade, okay? Well, the ice has to melt. That is positive. That takes energy in. How much energy is taken in? Well, that's the mass of the ice times the latent heat of fusion of water. Once the ice has melted, it has to heat up, and that's this term here. Mass of the ice, heat capacity of water, TF, minus the initial temperature of the ice at 0. When the ice melts, it turns to water at 0 degrees centigrade. So these are all of the heat processes that's going on. Because it's an isolated system, all of these heat exchanges have to add up to 0. So I can set this equal to 0. What the question asks is, what mass of steam do I need? So I just have to solve for MS. And you can see I've got it in here and here. So I'm going to take it out as a factor, shove those on the other side. And once I've taken it out as a factor, I can divide by all of this stuff in here. It's a bit messy, but there's the algebraic solution. And then I just have to throw all of these numbers in. And again, be careful with the calculation. There's a lot of numbers flying around here, right? Yeah, so kind of a slightly tricky problem, that one. You have to think about what's happening and write down a sort of an expression for each term. Okay, question 10. An iron boiler of mass 180 kilogram contains 730 kilograms of water at 18 degrees centigrade. A heater supplies energy at a rate of 58,000 kilojoules per hour. How long does it take for the water A to reach the boiling point? B to have changed all to steam. Okay, for the first part, I have to work out how much energy it takes to get both the water and the boiler from 18 to 100 degrees centigrade. So that's this bit here. The heat to heat the boiler up is the mass of the iron, the specific heat capacity of iron, Tf minus Ti, and then we have the mass of the water, heat capacity of the water, Tf minus Ti, right? So that's the heat needed to boil the water, and that's the heat needed to get the boiler itself, the iron in the boiler, up to that temperature, and the heat needed to get the water inside of the boiler up to that temperature. We can take TFTI out as a factor, and once I've done that, I just have to substitute some numbers in and get the answer. Okay? How long would it take? Well, power equals energy over time. Time equals energy over power. So there's the energy needed to boil the water, and there's the rate at which energy is being delivered by the heater. So put those numbers in, about 4 hours to get the water up to a boil. The second part then says, how long would it take to turn all of the water to steam? How long would it take to boil it dry? Well, in that case, the energy needed to vaporize the water will be the mass of the water times the latent heat of vaporization. So that's how much energy I would need to vaporize the water. We do the same thing, we divide it by the power, and that gives me 29 hours for the thing to boil dry. Okay. Question 11. At a crime scene, the forensic investigator notes that the 6.2 gram lead bullet that was stopped in a door frame apparently melted completely on impact. Assuming the bullet was shot at room temperature, what does the investigator calculate as the minimum muzzle velocity of the gun? Okay, so I think what we'll do here, we'll figure out how much energy it took to melt the lead, and then we'll equate that to the kinetic energy and solve for velocity. So the first question is, how much energy would it take to melt the lead? Okay, well, to melt the lead, the heat I need, I'd have to heat it up to its melting point and then add extra energy to make it melt, right? So we've got two terms here. This term here, the mass of the bullet times the heat capacity of lead, that's the room temperature melting point, that's the energy to get it up to its melting point, and then that's the energy needed to actually melt it. So it took 386 joules to melt the lead, to heat it up and then melt it. So kinetic energy is 1/2 mv squared, v is root 2ke over mb. There's my energy I just calculated. Whoops, it looks like I forgot a 2 in there. Oh dear me. Hang on a second, I'll go get a pen and make a note to correct that. I'll have to check. I honestly don't know if the answer's wrong, but I certainly forgot a 2. The answer could be right and I forgot the 2, or it could be that the entire answer is wrong. Anyway, I'll let you guys figure that out. It could be that there's a mistake there. I hadn't noticed that before. Okay, question 12. One end of a 56 centimeter long copper rod with a given diameter is kept at 460 degrees centigrade, and the other is immersed in water at 22 degrees centigrade. Calculate the heat conduction rate along the rod. Okay, so for question 12, we've got the thermal conductivity of copper. Remember in the last lab, you actually calculate this quantity for glass. And then here's our equation. Area, well, we're given the diameter, aren't we? So I guess I'm using pi r squared instead of pi d squared over 4. I've got K, I've got the area, I've got the difference temperature between the rods and the length of the rod. 93 watts would go through the rod. Okay. Question 13. How much power is radiated by a tungsten sphere with a given emissivity of given radius at a given temperature? Okay. Well, this is the Stefan Boltzmann law. The area of a sphere is 4 pi r squared. And so I've got the area of the sphere. Now, for the Stefan Boltzmann law, it's important that we use absolute temperatures. So I have to convert the 25 degrees centigrade into Kelvin. And then the TW, that's the temperature of the room or something. The walls, I guess that's the temperature of the walls, isn't it? That's why I've got a W there. That's the temperature of the walls in Kelvin. Okay. I'm wondering why I've got hang on. Oh yeah, -5 degrees. Yeah, that's kind of odd. The really cold walls, I guess. Okay, what is the net flow rate of energy out of the sphere? Okay, for the first part, how much energy does how much power is radiated by the sphere? This is the Stefan Boltzmann law. Emissivity, there's the sigma constant, Stefan Boltzmann we talked about. There's the area. There is the temperature of the sphere in Kelvin to the fourth power. Throw the numbers in, 71 watts. However, the sphere is radiating energy out to the walls, and the walls are radiating energy back to the sphere. So the emissivity is also tells us how well the sphere absorbs it. So to get the net radiated power, we have to take the difference between the temperature of the sphere and the temperature of the walls, like this. Okay, so you can imagine that that term is the emitted radiation, and that term there is the absorbed radiation. So when we put the numbers in, we find there's a net radiation of 25 watts. If you ever sort of if you think about, on a clear night, you're radiating energy out to space. Space is very cold, and no energy is radiated back. When it's cloudy at night, it's warm, right? It's never cold. If it's cloudy overhead, it's never really that cold. You wake up in the morning and your car isn't covered in ice. But on a clear night, yeah, your car is covered in ice because all the energy is radiated out to space, and none of the energy from space is radiated back because space is so cold. Okay, question 14. Approximately how long would it take? Let's change that. Approximately how long would it take 8.2 kilograms of ice at 0 degrees centigrade to melt when it is placed in a carefully sealed styrofoam ice chest of given dimensions with given thickness? Assume the conductivity of styrofoam is double that of air and that the outside temperature is 34 degrees centigrade. Okay, so what we need to do here is to determine how fast heat is coming into the cooler. The inside of the cooler is at 0 degrees centigrade because it's got ice in it. Once the ice is melted, it would start to heat up. But as far as we're concerned, we've got 34 degrees on the outside, we've got 0 degrees on the inside while the ice is melting. So we have to figure out how much power is coming into the styrofoam. We can figure out how much heat it takes to melt the ice, and then time will be just the heat required to melt the ice divided by the power that's coming in. Okay, so this is the area of the cooler. You can do a little sketch and convince yourself of this, but we've got the top of it and the bottom of it, the length times the width, and we've got two of those. You then think that you've got 4 sides, and the length plus the width times the height is 2 sides, and multiply it by 2, and that's the 4 bits. You don't have to work it out like that, but that's what it is, right? We throw the numbers in, we get the area of the cooler. The thermal conductivity, we double up the thermal conductivity of air, and then the rate at which power is entering the cooler is given by this equation here, our thermal conductivity equation, and all we have to do is put in the values, and 87 watts. That's the rate at which heat is flowing in. How much heat do I need to melt the ice? Well, that's the mass of the ice times the latent heat of fusion of water, and that's the heat I need to melt the ice. Power equals energy over time, time equals energy over power. Throw in the numbers, and then I get 8 hours, 47 minutes. Okay, so easy enough, but yeah, it's a nice question, that one. Question 15, I think all of these, there's no more calculations. Okay, question 15, if 2 objects of different temperature are placed in contact, will heat naturally flow from the object with higher internal energy to the object with lower internal energy? No, not necessarily. What determines the heat flow is the temperature, not the internal energy. So water, I think this is what I say here, water, for example, has a high internal energy. It's really good at absorbing heat. So if I had a kilogram of water and a kilogram of lead with the same internal energy, the kilogram of lead would be much hotter, right? Because it has a low specific heat capacity. So if I put the kilogram of lead in the kilogram of water, even though they have the same internal energy, the energy would flow out of the lead into the water. So it's the temperature which dictates the heat flow. I think I kind of answered the second part there as well. Okay, I think I answered the second part in answering the first part. Okay. Question 16. When a hot object warms a cooler object, does temperature flow between them? No, temperature doesn't flow, right? Heat flows, right? The heat is the flow of thermal energy. Are the temperature changes of the two objects equal? No, certainly not. Okay, it could depend upon the mass, right? You can imagine getting a red hot penny and dropping it into sort of a pint of beer, for example, right? Well, the pint of beer will not be appreciably warmer, but the penny would be appreciably colder. We don't have pennies anymore, do we? Oh, okay, a nickel then. You can have a red hot nickel instead. Okay, but what is equal though, as I say in the answer, what is equal is that the energy that came out of the red hot nickel would be the thermal energy that went into the beer. Question 17, the specific heat of water, I should say the specific heat capacity there. The specific heat capacity of water is quite large. Explain why this fact makes water particularly good for heating systems, that is hot water radiators. Well, because water is really good at storing thermal energy. There is a scheme, I know in Britain we used to have a scheme where electricity generated at night has no function, and so at night time you could heat a big tank of water up. Then in the daytime, when there is a sort of a large demand for electrical energy, you get your hot water and you use all of that stored thermal energy in the hot water to heat your house. Okay, so water, because it has takes a lot of energy to heat it up, makes for a good way to store this energy. Okay, and then when you pump the water around, it releases a lot of heat as it cools back down. Okay, why does water in a metal canteen stay cooler if the cloth jacket surrounding the canteen is kept moist? Well, this is vaporization. Basically, it's a little bit more involved than what we've talked about. But when you have vaporization from a surface, what happens is that the higher energy molecules escape. So when you have a material at a certain temperature, there is a distribution in energies. Not all of the particles have the same energy. You have some with higher energies. Our old friend James Clerk Maxwell worked this out, and it's called a Maxwellian distribution. So if you have a canteen covered in cloth, the highest energy particles can escape from that. They have the energy to escape. Well, if you take the high energy side of the distribution away, the average energy then goes down. So things cool down as water evaporates. Okay. Explorers on failed Arctic expeditions have failed by covering themselves with snow. Well, that's funny. If they failed, I assume they died, but maybe not. Why would they do that? Okay. There's two reasons. One I talked about. I mean, if it's a clear sky and you lie open under a clear sky on a night during the night time, you're trying to come into thermal equilibrium with space, and space isn't radiating anything back. So it's better to get under cover. I mean, you probably know that even places like the Sahara are really cold at night. Deserts are hot during the day, cold at night. During the nighttime, there's no clouds to sort of cover and stop the radiation radiating away. So the first reason is that it cuts down on radiation. The second reason is that snow traps air, and trapped air is a great insulator, right? If we manage to trap air, that works very well as an insulator. Okay, why is wet sand at a beach cooler to walk on than dry sand? So we've talked a little bit about this before. First of all, the sand undergoes evaporative heat loss. So as the water evaporates, it cools off. And also, the water, it takes a lot to heat the water up. So, it takes a lot of energy to heat the water up, whereas it doesn't take a lot of energy to heat the sand up. Okay? 22. Goose down sleeping bags and parks are often specified as so many inches or centimeters of loft. The actual thickness of the garment when it is fluffed up. Explain. Well, the rate of heat loss is inversely proportional to the length of the conductor. If you remember, we talked about the thermal resistance, right? And the thicker the actual loft, the greater the thermal resistance, the greater the opposition to the flow of heat. So you could specify the thickness of the loft. That really tells you how good a insulator it is, because the thicker the loft, the higher the thermal resistance. Microprocessor chips have a heat sink glued on top that look like a series of fins. Why are they shaped like that? The fins simply maximize the surface area, right? So if you look in computers, they have heat sinks. Usually it's metal. Metal conducts the heat away from the component, and then it has a large surface area, and either it's passively cooled, at which point we allow natural convection just to take the heat away, or you can get a fan and blow air over it, which is forced convection. We force the heat out of the circuit by using a fan. 24. Sea breezes are often encountered on sunny days at the shore of a large body of water. Explain, noting that the temperature of the land rises more rapidly than that of the nearby water. Well, okay, here's the daytime. The water has a high specific heat capacity. It heats up very slowly. It takes a long time to heat the water up. The land heats up quickly, right? The radiation doesn't penetrate deep. It's absorbed at the top layer. The top layer becomes very warm. The air here, because it's warm, rises. Well, that reduces the pressure here, and that sucks air in from the ocean, okay? And so we get this circulation pattern, and if I'm standing here, I feel a breeze coming in during the daytime. Now, at nighttime, what happens? Well, if this radiates out to space, it cools down very quickly, has a low specific heat capacity, whereas the ocean stays warm. So now the ocean is warmer than the surrounding air, and the ocean warms the air, that air rises up. So we get a low pressure here, and then the wind blows out, right? So you might notice this, it's not always true, it depends on a lot of other things, but you tend to get, if you live by the sea, on a hot day, you get a nice cool breeze blowing in, and on a cold night, you get a nice breeze blowing out, okay? 25. A 22 degrees centigrade day is warm, while a swimming pool at 22 degrees centigrade feels cold. Why? Well, quite simply, what we sense as temperature is actually the heat flow from our bodies. Okay, air is a very good insulator, so at 22 degrees centigrade in air, we're not losing much heat. 22 degrees centigrade in water, water's a good conductor compared with air. We lose a lot of heat and we feel cold, right? So it comes down to what we perceive as cold is actually the flow of heat out of our bodies. Question 26. So I like these questions, hey? Explain why air temperature readings are always taken with a thermometer in the shade. Well, if you have the thermometer exposed to the sun, the thermometer is trying to come into thermal equilibrium with the sun, and it's not giving us the air temperature. So you want it in the shade, so it's actually giving us the temperature of the air. Question 27, does an ordinary electric fan cool the air? Why or why not? If not, why use it? Well, if you think about it, if I have a fan whirring around, that's using electrical energy that has to be turned into heat. So if you have a fan on in a building, it's making the building warmer, it's making the air warmer. However, on a warm day, you sweat, and the air blowing across your skin increases the rate of evaporation, so you will feel cooler, right? So a fan will cool you down if you're sweaty, but it will generally warm the room up, right? Because it's a source of heat. How is heat lost from windows through the glass? Well, the glass allows radiation, okay? So heat can just radiate right out of the glass. There would be some conduction through the glass, I guess, and then also I guess the frame of the window would also allow heat. On modern windows, if you have aluminum windows or something, often you put what's called a thermal bead. So it's a plastic layer between the inside metal and the outside metal, and that stops the conduction, okay? But the glass will allow radiation to pass. Some modern windows have a are filled not with air, but I think with argon, because argon blocks the infrared radiation from radiating out of the window. B, 28B. How can heavy curtains reduce heat losses? Well, curtains have two effects. First of all, it blocks the infrared radiation from just going out of the window. But secondly, it acts to prevent convection. With single pane glass, the glass is cold and the air cools down and it sinks to the bottom of the room. Warm air from the top of the room comes around to replace it. So the air produces a convective cycle in the room. The cold window produces a convective cycle in the room. A heavy curtain stops this convection, right? It breaks up the convection. So curtains are very effective at keeping a room warm. Though no one likes them these days. No one really uses curtains anymore. 29. A piece of wood lying in the sun absorbs more heat than a piece of shiny metal. Yet the metal feels hotter than the wood when you pick it up. Explain. Well, because the metal is a good conductor of heat, right? Why does metal feel hot? Because it can conduct heat, and that heat is conducted to your hand, right? 30. The earth cools off at night much more quickly when the weather is clear than when cloudy. Why? I think I explained this one earlier. At night time, when it's clear, the earth radiates energy into space. Space is at 4 Kelvin. It effectively radiates nothing back. And so the earth cools down very quickly on a clear night. You'll notice this with a car, on a clear night, on a cold, clear night, the top of the car is frozen. But look at the doors. The doors of the cars tend not to be frozen because the doors of the car aren't pointing towards space. They're pointing toward a building or a hedge or something like that. And so the sides of the car try to come into thermal equilibrium with the hedge or the house. But the surfaces, the flat surfaces pointing directly up, will tend to freeze up. 31. An emergency blanket is a thin, shiny, metal-coated plastic foil. Explain how it can help keep an immobile person warm. We talked about this in the lecture, but a mirrored surface is a poor absorber of radiation. Obviously, you look in a mirror, it's terrible at absorbing radiation because it reflects it right back at you. That must mean if it's a poor absorber, it's a poor radiator. So when you cover yourself in a shiny mirror, basically there's no radiation coming off from that surface, right? So it minimizes the radiative heat losses. Okay, last question. Explain why cities situated by the oceans tend to have less extreme temperatures than inland cities at the same latitude. So you probably know that Vancouver, usually we make fun of Toronto, it's too hot in the summer and it's too cold in the winter. The reason is that our climate is stabilized by having the ocean next to us. So the ocean has a lot of thermal capacity. So in the winter, it retains heat, it keeps us warm, and in the summer, it absorbs heat, keeps us cool, right? So cities near large bodies of water, near the oceans, tend to have less extremes. Moscow, which is not by a body of water, which is very much inland, would tend to have hot summers and very cold winters, whereas we don't. Okay, that's the end of the problem set. I guess that's sort of the end of the material we're going to cover in the course. So let me know if you have any questions. I'm available by email, and hopefully it's clear what everyone needs to do. And thanks for being my audience, guys. It's been a slice. It's been kind of unusual. I've never had it like this before. Okay, so I'll sign off there.